You know, these Q codes, have they revised what some of those mean? I hear.
Well, very happy Wednesday evening to you radio enthusiasts. That's what we are. Radio kind of turns us on, at least it does me. It gets me excited listening to faraway signals and making contacts, QSOs, with other hams around the world. And we are in a beginning ham radio class. We're about halfway through. We are on chapter 5 of 9 in this book, the American Radio Relay League License Manual, the 5th edition. This is the book we work from. And we take a chapter a week and we focus in on the test questions. Test questions? You get your amateur radio license in the United States by passing a multiple choice test, 35 questions. And if you get 74% right, you pass. You're a licensed amateur radio operator, you'll get a call sign from the FCC, and you can join in on the fun. You don't need a license to listen, but to transmit, to make contacts, to make QSOs, yeah, you need the license. And the technician is the beginning level license. That's what we're all about here. I'm your instructor, Gary, ham radio call sign Whiskey 4 Echo Echo Yankee. I'm kind of pumped up tonight. The chapter title is Amateur Radio Equipment, and we're going to talk about modulation to get us started. So modulation, what is that about? Well, you might remember from last week we talked, no, that's a bad slide. RF equals radio frequency. And when we talk about RF signals, we're talking about radio frequency signals of any type. So here we're looking at a spectrum display of amplitude. Let me get my laser pointer turned on over here. Amplitude of signals on the vertical and frequency here on the horizontal. So here's a really strong band of radio frequency signals. Here's another strong band. So this is a spectrum display. Here's clear spectrum where there's no signals going on. So each of these signals, the reason they're being transmitted is to convey information. And modulation is the way we add information to a radio wave. Because if we just have a transmitter and put a carrier on the air and don't do anything with that carrier, okay, we can hear that there's a carrier there, but that doesn't tell us anything. And so the most basic form of adding modulation is Morse code, where you turn on and off that radio frequency carrier in a pattern that is known at the opposite end. And so using a Morse code key like this adds information to that radio frequency carrier. Okay, Morse code on radio, what we were talking about there, it's abbreviated as CW, or continuous wave. It has to do radio's over 100 years old. And when they first got started, they were using motor generators and sparks. Some people were making transmitters out of old Ford Model T magneto transformers, and they would spark your signal in the Morse code pattern. Well, a spark transmitter generates a wide band of frequencies. Later on, they came up with vacuum tubes and oscillators and the way to have a pure signal, and that's what we mean by continuous wave. It's a wave that's on just one frequency. You could say that Morse code makes it discontinuous wave, but okay, that would be confusing the issue. CW transmissions have always been said to be the farthest distance for the amount of power that we're using. That's actually been overcome now with computers and a new technology. We'll talk to you about that. A CW transmitter generally emits energy on or about one frequency. Just the mere fact of keying the transmitter on and off, though, does generate a signal that is centered around the transmitter frequency. We call this bandwidth. So here we have the transmitter, the frequency of the carrier. This is the transmitter is on this frequency, and as we modulate it with on and off from Morse code, it widens the output, and so this is the 50% power point, also known as the minus 3 dB power point, and we would say that this would be the bandwidth of this signal. We don't worry about this down here. This is no signal level here. This is peak signal up here in the half power point. That sets the bandwidth. For Morse code or CW signal, the bandwidth of the signal is about 150 hertz. So it's a very narrow band signal, and it's all, on the other end, on the receiver end, you can use very narrow receive filters to eliminate all of the other interference and noise, which makes it easier to hear weak signals. All right, so we got started with Morse code. You think about the Titanic. They were using SOS for the first time. Previously, the distress signal had been CQD for CQ distress. But what about voice signals? Well, voice signals were experimented on, and amplitude modulation was the first voice mode that was successfully used. And with amplitude modulation, what you're doing is you have your voice signal or low frequency signal, the modulating signal as it's indicated here, and you have a much higher frequency radio carrier whose amplitude, you see, up and down, is varied in concert with the modulating signal. So you're changing the amplitude of this signal. We're looking at this signal in what we call the time domain. We're looking at it as an amplitude here and time. So this is what you would, if you had an oscilloscope and we're looking at the transmitter output, this is the kind of signal that you would see. Now, another way that we look at signals is in the frequency domain. And so this is what a frequency domain pictorial would look like for an amplitude modulation signal. You have the main carrier frequency, and then the modulation adds bandwidth to the lower and to the upper. We call this area the lower sideband. We call this area the upper sideband. And this is in the frequency domain, or looking at the frequency. And here's another look at that. For communication signals that we use in ham radio, we say that the bandwidth is 6 kilohertz. That's sufficient to get good voice communications. And so there's 3 kilohertz being used here on the lower sideband, 3 kilohertz here on the upper sideband. Another look here. Lower sideband, the radio frequency carrier, and the upper sideband. So this is an AM or amplitude modulated signal looking in the frequency domain. We're going to look at an actual signal coming up here in just a bit. And we're going to do so using my Flex 6600 radio. You can see the radios, the yellow arrow is pointed at it there. That's in my workshop ham station down below us here. And so now we're going to go for what I call a maestro moment. We're going to try to take a look here at a 40-meter signal, an amplitude modulated signal on 40 meters. So let me walk over to the maestro briefly. Hi, here I am. So the maestro, let me walk over here, is this box right here. This is the maestro control unit. And you have a big knob. You can change the frequency that you're receiving. And it's got a bunch of other knobs and controls. And it's got a spectral display on the front. And what we have done is enlarge the spectral display over here on the monitor. So we are on the 40-meter band, a 7 megahertz frequency. If you've got a color chart, or if you use the one in the book, you'll see that 40 meters is 7 megahertz. And 7 megahertz of the 40-meter band is a shared band. It's a band that we as amateurs can use, and also international broadcasters can use. International shortwave broadcasting is still a thing. It's how I got into ham radio, was listening to international shortwave broadcasts. And it's also the reason I ended up working for Voice of America, which is the US government's international broadcaster. And what we have here that we're looking at is an international broadcast signal. This is the radio frequency carrier, the center part that we saw. And the sideband, the lower sideband, actually we say that for a ham radio it extends 6 kilohertz wide. That's what this is demarking. But they actually, for international broadcasts, can go plus or minus 5 kilohertz, so it's 10 kilohertz wide. This is an international broadcast station. I'll tune up the audio here just to see if we can hear it. Chinese? So what it is not important, but I just wanted you to see that this is an AM signal. So let's go back, and I'm going to do a little annotation over here on the iPad. So again, you can see here on the iPad, this is the Maestro display. This is the frequency that the radio is tuned to on its VFO-A. And the top part of this display, above this yellow line here, this is the amplitude of the signal as it's bouncing around. Down below is what we call a waterfall display. This is a display of signal strength over time, and it's going out as far as 20 seconds. So you can actually see where signals were even after they've been. So this is a common thing on amateur radio transceivers. The ICOM IC7300 has this kind of display. Flex is known for their very high quality displays. And so what we're seeing here is an amplitude modulated signal with its lower sideband over here and its upper sideband up here, and the carrier up there, the three signals that we saw on our chart. And if we go back to the laptop, you can see, again, here's another view, or kind of beating it to death here, the original audio, and then we have the amplitude modulated signal with lower sideband, carrier signal, and upper sideband. Well, what if we could eliminate two of the three components? If we could eliminate one of the sidebands and the carrier, we would be left with just the other sideband. So here's what an upper sideband signal would look like without the carrier and lower, or here's what a lower sideband would look like without the carrier and the upper. And so single sideband is the most common voice mode for transmission in HF, VHF, and UHF. The little HTs that you they use something called frequency modulation. So they're not using amplitude modulation, and they're not using single sideband. But we want to talk just about single sideband for the moment. The beauty of single sideband is that if you've got a 100-watt radio, that 100-watt radio has to amplify all three, lower sideband, upper sideband, and the carrier, if you're in the AM mode. But if you eliminate everything but one of the sidebands, the upper or the lower, or lower and upper, then the 100 watts can be used to amplify just the sideband modulation. You need a special receiver at the far end in order to demodulate that, or it won't sound right. But single sideband was championed by Collins Radio and the Strategic Air Command because they needed a way to talk to their long-distance bombers from far away, and amplitude modulation wasn't cutting it. But single sideband came to the rescue, and it's really it was innovative, but it was also contentious back when it was first introduced in the amateur radio bands. A lot of hams said, that's not ham radio. Now it's the most popular way, although AM signals still do exist. If you'd like to see more about the military's take on single sideband, there's a video here, there's a URL, you can go ahead and take a look at it. So we said that the bandwidth for an AM signal for communications purposes is 6 kilohertz. For a single sideband signal, it's half of that, or 3 kilohertz. All right, let's go back over to the Maestro just for a second. I want to look for some single sideband signals. So here we are on the same radio, same signal that we were on before. We're in the AM mode. I'm going to tune the radio, though, now down to some single sideband signals. Oh, of course, they went away. You hear that? If you can hear it, it sounds garbled. It's distorted. You can't. What the heck are they saying? That's because we're trying to receive single sideband in the AM mode on a radio. It won't work. But if we take the radio and we go to lower sideband and I retune it, okay, they're speaking Spanish. I can move this over. But here is a lower sideband signal. Actually, two of them. There's one there and there's one there. But we are able to demodulate it. Note there's no upper sideband signal. So this is a single sideband signal, lower sideband. Let me turn it down so that we don't have that competing. So that's on the 40 meter band. Let's see about the 20 meters. Let's see if 20 meters is open now. 20 meters is 14 megahertz. Oh yeah. Oh, wait a minute. I think I'm still on lower sideband. Let's go to upper sideband. No, I was on upper sideband. They're transmitting on lower sideband. That's not normal. Okay, that's a weaker signal. But anyway, here is an upper sideband signal on 20 meters, 14 megahertz. Oh, here's another stronger one coming up over here. Oh, and he went away. So anyway, I just wanted you to see some signals on some of the bands, and we'll be playing around later in the class and maybe try to make some contacts as well. So you notice we were unable to listen to that one signal because I was on the wrong sideband. There's a convention, there's a standard as to which sideband should you use. If you're transmitting on a frequency below 9 megahertz, the convention is that you will use lower sideband. If you're transmitting on a frequency above 9 megahertz, you'll use upper sideband. There was a technical reason for this back in the day when people were building transmitters that could operate on 80 meters and 20 meters, and it allowed them to share some circuitry. But now it's just by tradition and by convention. One thing that on all of the bands, and if you look at the color charts, come on back to me just for a second if you would, Bruce. The color charts, they will have on the 40, 80, 40, and 15 meter bands various allocations for technician class, for general class, for advanced class, and for extra class. There are some limitations. You need to keep that in mind. So, for example, we want to watch out the band edges. This is 20 meters, 21 megahertz. 21450 is the top end of the amateur 15 meter band, if you look on the color chart. So we do not want to be transmitting above 21450. So knowing that our signal is 3 kilohertz wide, we want to have that indicated number on our radio to be 3 kilohertz below the band edge, or 21.447. We want to keep the modulation on our minds here so that we don't transmit out of band. It's not something you're going to have to really worry about so much until you get your general class license, but I want to introduce this concept as well. All right, so that's AM and single sideband, and we talked about CW or Morse code to start it out. Now let's talk about frequency modulation. So with frequency modulated radios, the voice signal is the same kind of thing. All right, here's amplitude modulation, what we've seen already. With frequency modulation, the amplitude stays constant. The output of an FM radio is 100% all the time as far as its amplitude. If it's a 5-watt radio and you hit push to talk, it's going to transmit 5 watts all the time. What it will do, however, is change the frequency of that signal. It will deviate it from a lower frequency to a higher frequency to a lower frequency in concert with the audio modulating signal. So here's a little bigger view of that. You can see the amplitude modulation change here that we talked about. Here with FM, the amplitude stays the same, but it's the frequency that varies. FM is allowed on frequencies above 29.5 megahertz. So the very top end of the 10-meter band, all VHF and all UHF can use FM. FM has some advantages. Again, you're transmitting full power all the time, so you'd think that might get through better, but there are some characteristics that doesn't always make that the case. Another thing with FM, the bandwidth is not as narrow as single sideband. We said the single sideband bandwidth was 3 kilohertz. For FM, it's between 10 and 15 kilohertz. So you need a wider bandwidth area available to contain that signal. You got to keep that in mind when you're getting close to a band edge or something like that. The other thing about FM, it's not the transmission, but it's the receivers. FM receivers use FM discriminators, and the discriminators will capture the strongest signal and actually block out any of the weaker signals. So if there are two signals, two stations on the same frequency and you're trying to hear them both, you won't. You'll only hear the stronger signal to you, which is one reason why aircraft still use amplitude modulation on their radios, because in that case they can be on a common frequency and you'll hear multiple signals and they'll be able to at least be noted, oh, there's another signal coming in. With FM, it just wouldn't be heard because of the discriminator in the receiver. All right, moving on. Let's go a little back in time. I don't know how old you are. I'm too old because I do remember this. The days of bulletin board systems and dial-up modems and computers. My first computer was a Commodore C64, as many folks were, and I had a modem, and I was able to connect into a local bulletin board system in my area. This predates the internet, and the bulletin board would serve you up some information or recipes, or you might be able to leave mail and retrieve mail in an early form. So this was the early days of computer telecommunications. And hams, okay, we like to take this wire-based system and put it on radio. So hams came up with packet radio. And packet radio used a computer or even a dumb terminal to be able to connect up to a box that was called a terminal node controller. This would connect up to a little FM radio, like an HT, and going out to an antenna. And it would have audio from the TNC to the radio, audio from the radio back to the TNC, and a push-to-talk control. All three of those were enabled, and you would be able to send computer signals, packets, out on the radio to be received by your friend's TNC maybe 10 miles away. And the TNC would capture the signal, would tell the transmitting station, I got it, send another, or it would say, no, I didn't get it, send it again. And that's all information that was contained in the packet. The packet had some parity information in it that would do some error checking, and if it didn't all check out at the far end, it would say, oh, that didn't work, you need to send it again. So packet radio using FM to transmit on VHF. 2 meters was the popular frequency band in my area for packet radio. That's FM, changing the frequency of a signal. There's a cousin to FM. It's called phase modulation. It's a type of frequency modulation. The big distinction with phase modulation is that not only does the amplitude of the modulating signal change the frequency, but the audio modulating frequency, the higher frequency, actually changes the frequency deviation more than a lower frequency. It doesn't change it as much. So that's the big difference between FM and phase modulation. Receivers that can receive FM can also receive phase modulation because they're so close. All right, another form of modulation, different than what we've talked about before, is something called phase shift keying. And it's a digital modulation process that conveys information by changing the relative phase of a carrier signal. So before we've been changing the frequency and we've been changing the amplitude. Now we can change the phase. So a sine wave that was going up and down might now go up and up and up and then down. You can do that by creating this sort of complex carrier. What this does is the same way that voice modems back in the day. Remember the first modems you used to be able to buy for computers were 300 baud, very slow. And then they went to 1200 baud, 2400 baud. They were using phase shift keying in order to use the same bandwidth, the phone line, but to get more information through and at a higher rate. And that utilizes phase shift keying. We do phase shift keying also on the radio as well. A lot of terms here. Frequency shift keying is another that is associated with radio teletype. And of course, if you're as old as me, you remember the old news shows used to have the teletypes from UPI and AP, clacking away in the background of the newsroom. Well, that same thing can be done over radio, and it's still active today. Radio teletype is a mode that amateur radio operators use. And they use it by actually transmitting two frequencies spaced a standard apart, usually 170 hertz apart. Here's one of those frequencies, and here's another of those frequencies. And the signal alternates back and forth between these frequencies in a pattern. And that pattern is the Baudot code. We're not going to go complex into that. We do that in the general and extra class. But I just wanted to introduce you to these modulation modes. So let's review a little bit. Morse code goes the farthest for the power used. That's been the standard. FT8 we're going to introduce you to is actually a little bit more efficient now, but okay. It used to be a test question, and that's why we had to include it, and I just want to include it now for posterity. Single sideband is the voice mode that goes the farthest. You'd think, well, FM should go the farthest because you're full power all the time. No, because of the complexities of reception, it doesn't. So single sideband is the voice mode that goes the farthest. There is digital voice modes on VHF and UHF, and also HF. Not as popular on HF, but it does exist out there. FM, the things that we use for our small handy talkies, has the clearest voice quality. FM phase frequency shift keying, phase shift keying, and digital modes can transmit text files. And packet radio uses FM on VHF and UHF frequencies. So we've introduced you to a bunch of new modulation modes. There's more information on these in the book, and if you follow some of the links here in the presentation. I've been very fortunate. Coming back to me just for a second. I mentioned that I work for the Voice of America, but before that, I worked as a broadcast engineer for a television station, a couple of them, in Michigan. And I was a broadcast maintenance engineer. I get to fix stuff at the station. And so fast scan analog television was my thing before I joined the Voice of America. Well, fast scan analog television still exists in amateur radio. So if you remember your old CRT TV, come on back to the laptop, yeah, this one. Well, you could still use it in amateur radio. So amateur radio fast scan TV is the same as the old analog TV signals that we used to use. It's the NTSC system, which stood for the National Television Systems Committee. It's used by amateurs in UHF and above. I'll tell you why here in just a second. Interestingly, it uses AM modulation, as did broadcasters. But with part of the lower sideband removed or suppressed. That's why we call it vestigial sideband. Now, CW's got a bandwidth of about 150 hertz. AM signals have a bandwidth of about 6 kilohertz. Single sideband signals have a bandwidth of about 3 kilohertz. FM transmissions have a bandwidth of about 10 to 15 kilohertz. TV has a bandwidth of 6 megahertz. It's really wide, and that's the reason why it's only used on UHF and above bands, because those are the only bands where we have the bandwidth to actually be able to transmit these signals coherently. So just keep that in mind. All right, we made it to questions. We focus in on the test questions. These are the actual test questions you will see on your test, and the actual answers, except the answers won't be in the same order. So don't memorize A, B, C, or D. That won't do you any good. All right. Which of the following is a form of amplitude modulation?
C, Charlie.
Yes, single sideband is one of the two sidebands that you have in AM, so it's a part of the amplitude modulation family. And what type of modulation is commonly used for FM packet radio transmissions?
Alpha.
FM, yes indeed, or phase modulation, but the little handy talkies can be used for packet. And which type of voice mode is often used for long-distance weak signal contacts on the VHF and UHF bands, Tom?
Charlie.
C.
Yeah, I called him out on, well, we had a nice email discussion about this. That's why I called him out. All right, so which type of modulation is commonly used for VHF and UHF voice repeaters? Repeaters.
Delta.
Yeah, repeaters, like the handy talkies, they use FM. And which of the following types of signal has the narrowest bandwidth?
C.
CW, or Morse code, 150 hertz. Yes, indeed. And which sideband is normally used for 10-meter HF or VHF and UHF single sideband communications? So think about this. 10 meters is 28 megahertz. VHF is 50 megahertz and above. UHF is 300 megahertz and above. So they're all above 9 megahertz. What do you think they should be using? Upper sideband, exactly. And what is a characteristic of single sideband compared to FM?
Charlie.
Yes, single sideband signals have a 3 kilohertz bandwidth. FM have 10 to 15 kilohertz bandwidth. So what is the approximate bandwidth of a typical single sideband voice signal? Oh boy, I just said.
Just answered that one.
Yeah, I
D.
did.
Bravo.
Yep, 3 kilohertz. And what is the approximate bandwidth of a VHF repeater FM voice signal?
Charlie.
Charlie,
Yep,
yes.
between 10 and 15 kilohertz. Very good, you're doing great. So what is the approximate bandwidth of AM fast scan TV transmissions?
Bravo.
Yeah, the old analog standard NTSC, which we said stood for never twice the same color. All right, what is the approximate bandwidth required to transmit a CW signal?
Bravo.
Remember, it's 150 hertz. It's the narrowest of signals we've talked about so far. And which of the following is a disadvantage of FM compared with single sideband?
Bravo.
Because of the discriminator in the receiver, it'll only capture, it's called the capture effect, the strongest signal. So only one signal can be received at a time. And what is CW?
D.
Yeah, another name for a Morse code transmission. Very good. You're moving right along. All right, if you would mute yourselves as we go along. I don't have a producer tonight to do that. Would help me out a lot. All right, section 5.2, transmitters and receivers. So some folks might be familiar with citizens band radio. Here's an old CB. I don't know if this is 23 channel or 40 channel. They came along. They have a big knob, but if you tune that big knob, it goes click, 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 click. Because the radios were synthesized or used crystals so that you would transmit only on one specific frequency. And then you move on to the next specific frequency, and then to the next specific frequency. With amateur radio operators, we have what we call the big knob. And we can, this is the variable frequency oscillator control. We can actually tune to any frequency in the band. And so here's the spectral display of an ICOM 7600. This is kind of like we saw with the Flex, a little smaller. This is the frequency that the VFO is tuned to, and depending on the modulation mode selected, it depends on where the signal is actually going to be generated. Now, on HF radios and on CB radios, you will find squelch controls, and they're not as common on HF transceivers as they are on CB or even HTs. So a squelch control, well, if we go over to my handy talkie, let's go to the calculator cam. I got out the venerable Baofeng UV5R. I got a bunch of these sitting downstairs, all right? I'm not going to transmit on it, but right now the radio is just sitting in receive, and it's nice and quiet. We're not hearing anything. That's because the carrier squelch function is working in this radio. There's no transmission coming from the repeater. It's tuned to the Caesar's head repeater, but there's no transmission coming into it right now. I can turn squelch off on this radio by pushing on the button here on the bottom. Do you want to be listening to that all the time? So you see, squelch has a purpose. It keeps the radio quiet until a transmission comes through. So squelch is important, and it's used with VHF and UHF HTs and mobile radios, very common. Less common in HF radios, although here's an Alinco. I have this radio actually in my truck, and it does have a squelch knob, so it can be utilized. And so if you don't want to listen to all that background static all the time, that's fine. There are different kinds of squelch, and we're going to go into that here in just a second. So mobile radios and handy talkies make the most use of squelch control. This is a Kenwood V71. I have one of these in my truck as well. Here's the Baofeng. We looked at one of those as well. So I mentioned carrier operated squelch. That's when a radio signal comes up on the frequency, the radio will open up for any carrier. It doesn't care. There's also selective squelch, which can be called CTCSS, PL, or tone squelch, where the radio transmits a very below the audible hearing range, a subaudible tone that the radios can detect. And you can program your radio to only open up when that tone is there. Radio repeaters commonly use CTCSS or PL tones. You can't get into the repeater unless you program your radio properly with the proper PL tone, for example. CTCSS and PL are the same. Motorola called it PL, and I think it was GE that called it CTCSS. There's also a third variant, something called digital coded squelch. I don't have a lot of experience with it personally. It's not used by any repeaters in our area, but it can be. It's another selective squelch mode. Well, how do I know how to program my radio to get all this information? Well, there are repeater directories you can find at Hamfests. Somebody was commenting they might go to the Dalton Hamfest this weekend. There'll be a vendor there selling repeater directories, so you can get a book. There's also apps. One that I like is a Repeater Book. It's a free app for iOS and for Android, Repeater Book. They also have a website, repeaterbook.com. And you can put your zip code in, or if you have it on your phone, it uses the GPS in your phone, and it will tell you the nearest repeaters to your location. And you can have it set up for just 2 meters or just 70 centimeters or whatever band you want, and it'll have all of the information you need as far as the location, the PL tone, input frequency, output frequency, all of the information you need to program your radio. So that squelch that we heard on the radio there, it makes the radio quiet, but one disadvantage of that is that also a very weak signal might not get through. So in order to, if you know a very weak signal is going to be coming on frequency, your friend is up on a mountaintop 100 miles away, and you know he's going to be transmitting a weak signal to you, turn the squelch off. That way you can hear him in the noise. Because if you have the squelch on, he may never break your squelch, and you may never hear him whatsoever. So for weak signal reception on FM, you need to turn the squelch off. So we mentioned that modulation is adding information to a radio carrier, and that there are various input devices that can add this information. We talked about the Morse code paddles. There are also various kinds of different keys and paddles that can be used. For Morse code, there are even Morse code keyboards that you can actually type on. There are also computer programs now for modern computers that you can interface with your radio and type away, and it'll send Morse code. There are also CW decoders. Some are better than others, but it's better. The best CW or Morse code decoder that exists is right between your ears. The human brain, it's like another language. It's like learning another language. But once you learn it, you can become fluent in it. And that's the best CW decoder. And of course, microphones, if you're like me and you like to talk. I'm a single sideband guy. That's what I like to do most of the time. If you are going to do Morse code, something I'd recommend is getting, if the radio doesn't have one built in, is getting something called an electronic keyer. An electronic keyer is coupled with a paddle. This is the bencher paddle. And you move the paddle one direction, you get a dit. You move the other paddle over here, you get a da. You squeeze them. It's called iambic keying, and it alternates between dits and das. It's a whole thing to learn how to send Morse code using this kind of system. Now, the electronic keyers were external for a long time, and then most manufacturers have built them in to modern radios now. So any of the modern radios you would buy would have a keyer built in, and all you'd need to do is add a paddle like this, and away you go. Now, you may not want to do Morse code, but okay. Now, if you want to do voice like me, here's a little heads up. So the connector there on the left is called an 8-pin Foster connector. It's probably one of the more common connectors for medium older radios. Kenwood used it, ICOM used it, Yaesu used it, others used it as well. It was not standardized. So the pin layout is different between various manufacturers. So I just caution you that if you have a radio and you got an ICOM radio and you've got a Yaesu microphone and it's got the same connector, and you say, I'm going to plug it in there, it might not work. You don't want to necessarily do that. You want to, learn more about how the pins go, where the microphone element is, where the push-to-talk lines are. Just heads up about that. Actually, a lot of radios now are using RJ45 or the smaller phone connectors for microphone inputs as well. So it's a whole thing. There are adapters that are sold. Heil Radio has a whole line of 8-pin Foster adapters here to go to just a microphone input and a push-to-talk input here on sub-miniature and quarter-inch jacks. It's a whole thing. Find a friend who's an electronics technician, and they can help you get your system up and running. You get your microphone plugged into your radio and you're ready to go. But keep in mind microphone gain. It's like, the Goldilocks and the Three Bears. Too little, that's not enough modulation. Too much, Well, that's way too much modulation. You want to be just right. So microphone gain, just know that too much gain will cause distortion. It'll also cause background noise. You know, your wife is working in the kitchen, or your husband is working in the workshop banging on something. It'll pick up all that noise as well. So you work on the microphone gain. Are you a nerd like me? I love ham radios because they've got all these knobs and buttons and things that I can push and manipulate. Here's an Elecraft K3 front panel, and yeah, it's exciting. Note the 8-pin Foster connector here for the microphone input. You got to make sure you got the right pinouts. So on a transceiver like this is a high frequency transceiver. Come back to me just for a second, Bruce. I mentioned I got started, listening, hang on. Got started in radio listening to international shortwave broadcasters. Pardon me. And so receivers have a lot of knobs, but transmitters add more knobs as well. My introduction to radio was on the HF bands. Nowadays, your introduction to ham radio is more on the VHF and UHF bands, but they still have test questions with regards to HF, so that's why we're going over this. Okay, so some transceiver terms that we want you to know about. The big knob, the thing we saw before, that's also known as the variable frequency oscillator. That's where you're tuning the radio to the frequency that you want to receive. Most HF transceivers are what we call multi-mode radios. They're radios that can send and receive AM, single sideband, CW, FM, radio teletype, and various data modes. And sometimes you push a button to change the mode that they're going to be operating in. Most transceivers have memory channels. They're slots where you can store preset frequencies and mode settings. So if you've got a net that you want to join on a regular basis, you can put it in memory and push a button and boom, you're right on frequency. Most HF transceivers are multi-band. They don't operate on just one band. They may operate all the way from 160 meters up to 6 meters, so a lot of bands. Also tuning. You can use a memory channel. You know, we mentioned that before. You can change frequencies by using the VFO knob. And a lot of radios also have direct keypad entry, where you can key in the frequency just by pushing on the keypad, and boom, you're there. So no, those are all valid ways of changing a radio's frequency. Now, on receivers, some terms we want you to know about. How sensitive is the receiver? It's the ability of a receiver to detect a weak signal. That's its sensitivity. And then going along with that is its selectivity. It's the ability to separate one signal from another that are very close in frequency. So these are important things to have with receivers. And receiver controls, we have on our radios an AF control. AF stands for audio frequency. It's a volume control. Okay. If we have an AF control, sounds cooler. A lot of older radios had something called an IF gain control. Or IF is intermediate frequency. It's a part of the internal amplifiers inside the radio. Most modern radios don't have that anymore. Now, we do have IF filters. You can set the bandwidth of the reception filter to match the modulation mode. So for CW, very narrow, for single sideband, wider, and for AM, even wider still. Radio frequency gain control, yeah, this is important. Sometimes you want to turn down the gain on your radio. You can do it with the RF gain control. You can also do it with an attenuator button. You can add an attenuation. If you're in the presence of very strong signals, it can help the radio deal with the strong signals. And also notch filters are handy. If you've got an interfering signal coming up on an adjacent frequency, then you can adjust the notch filter and get rid of it, eliminate it. It's kind of cool. Now, when we're using filters, I remember I said you want to match the transmitted bandwidth. So if you've got a CW signal, you want a narrow bandwidth filter. If you want single sideband, you want a wider filter. And if you want AM, you want a wider still. You match the transmitted bandwidth for the best reception, you get the best signal to noise ratio. Another important control on your radio receiver that a lot of old timers used to disdain using was the automatic gain control. AGC keeps very strong signals that might suddenly come on the frequency that you're listening on from blasting out your ears. A lot of old timers would run their radios max gain, max volume, headphones, which is why a lot of them don't have any hearing anymore. So use AGC. Fast AGC is good for single sideband use. It keeps audio at a constant level when a really strong signal comes in. I mentioned a net earlier. Come back to me just for a second. Bruce is active in a net operation on 40 meters every morning. The Treasure Coaster's net, thank you. So they meet on a certain frequency every day, every morning on 40 meters. And so he might have that programmed in memory on his radio. Now, one of the participants in that net, though, one day might be slightly off frequency. And, you know, okay, you could turn the big VFO, but then you're going to be off frequency the next time you transmit. Another control that receivers have is something called receiver incremental tuning, or RIT, which just changes your receive frequency. It keeps your transmit frequency on the net frequency. Come back to the laptop if you would, Bruce. So if you use receiver incremental tuning, we could say it's fine tuning for reception. Keeps your transmit frequency unchanged, and a single sideband voice can be made to sound better if you use the RIT signal control to match if the other station is slightly off frequency. So keep that in mind. Receiver incremental tuning. And on receivers, whether it be a digital one like the Flex or an old analog system, typically they're going to have an S meter. An S meter stands for a strength or signal strength meter. And this is the typical calibration going from S0 up to S9. And after S9, it's actually in dB, plus 10 dB, here plus 30 dB, plus 60 dB. Each S unit is nominally 6 dB. Every manufacturer is different, but that's the standard. That's what we go by typically. It may not be strictly calibrated though on some radios, but just know that that's what this is all about. It's indicating received signal strength. And so one S unit from S5 to S6, for example, is 6 dB power change, or that's 4 times power change. So if the guy at the far end is running 100 watts and he's S5, in order to get up to S6, he's going to have to be running 400 watts. It takes a lot of power to get up even just one S unit. Another control on receivers, especially important if you're going mobile and trying to listen to amplitude modulation or single sideband signals, that's a noise blanker. It eliminates ignition noise or sometimes electric fence noise, things like that. What it does is it actually squelches the audio during detected noise peaks. So here's a noise peak on a signal you're trying to receive. The radio is able to automatically eliminate it, and then you can hear things more intelligibly. So that's what a noise blanker is all about. You don't want to leave it on all the time, but if you've got a special need for it, turn it on and it might help you out. I don't have a picture of it. My very first radio for amateur radio was a Heathkit Mohawk. Huge tube type radio. Weighed like 100 pounds. It was, oh baby. And with vacuum tubes radios especially, their sensitivity as you went higher in the bands, it was good on 80 meters and 40 meters and 20 meters. But 15 and 10, it didn't hear so well. And what I had to do is I had to add a receive preamplifier. That's what this is. This is an RF, or radio frequency preamplifier, and it installed between my antenna and the receiver, between my vertical antenna that I had at the time and my Heath Mohawk. I had one of these. This is also a tube type unit. It had a range selector switch here. You select it for the approximate band, and then you tune this for maximum signal strength. It helped. It allowed the radio to hear on 15 and 10 meters much, much better. So that's what an RF preamplifier is all about. Nowadays, in modern radios, they have RF preamplifiers built into the radio. So you probably won't need to add one of these, but you need to know that it exists. So we've been talking about receiver terms. Now let's talk about some transmit terms. We looked at the mic gain control. Remember, Goldilocks, we want to be just right. There are also other speech processor settings, compression, equalization, things that can be used to make your signal sound better on the far end, or to raise your average power level of transmit. Again, too much of a good thing is not a good thing, so use it in moderation, but it can help you. Also, your RF power level control. So this is a Yaesu, I think it's a 950, and it's a 100-watt radio. But we have the ability, when you get your general class license on HF, to transmit up to 1,500 watts. Well, this radio won't do 1,500 watts, so what you have to do is put a power amplifier after it. And that power amplifier is going to have a certain range of power it likes to see, typically 30 watts, no more than that. And so you need an RF power level control to turn down the 100 watts on your radio down to the 30 watts that an amplifier like this is an Elecraft KPA 500, a 500 watt amplifier. It would typically take 25 to 30 watts to drive it to full 500 watts power. So an RF power amplifier, also known as a linear power amplifier, it increases transmitter power possibly up to the full legal limit of 1,500 watts. Now you can get power amplifiers for VHF and UHF as well. This amplifier will go up to 6 meters, but if you want to go to 2 meters or 70 centimeters, you're going to probably be looking for a power amplifier that looks like this. These are what power bricks, or they're power amplifiers. These have mode switches on the front. And it's important to note, for single sideband, you select so that it's operating in its linear mode. For FM signals that don't care, you can put it up in the FM position and it operates more efficiently. They have this switch, but it switches it between linear amplification and non-linear amplification, and it's important to note that you get the switch in the right position for the kind of modulation that you want to use. When we're talking about maximum output power, we're talking about something called average power and peak envelope power. Continuous or average power stays constant for CW, FM, radio, teletype, and data. You're just turning them on and off, but the output power stays the same. Whereas with amplitude modulated signals, AEM and single sideband, the amplitude varies greatly, and so we look at the power level from peak to peak and use that to calculate the output power. So that's why our maximum output power is said to be 1,500 watts peak envelope power, PEP. And we won't talk about how to calculate that here in this class, but we do that in the general and the extra class as well. So with your transmitter output, here's your transceiver. Remember, transceivers combine transmitters and receivers in one box. We might have a linear amplifier, maybe a low-pass filter, a standing wave ratio bridge to measure antenna matching, and then an antenna tuner and out to the antenna. This is a block diagram of a possible setup that you might have. Now, I mentioned that the amplifiers don't want to see more than about 25, 30 watts into them. What happens if you transmit too much? Well, you cause clipping. You overdrive the amplifier. The amplifier will go up to whatever it can do, and it can't do any more, and so it starts cutting off the tops of the peaks. And when that happens, you get distortion. you get spurious output on frequencies well away from where you want to be having output. And harmonic output happens as well. If you're transmitting on 7 megahertz and you overdrive an amplifier, all of a sudden you'll have signals on 14 megahertz times 2 or 21 megahertz times 3. All of the harmonics of that fundamental frequency will also start appearing on places that you don't want them to appear. So that's why you always got to keep in mind you're not overdriving an amplifier. And when you're doing testing with a scope or things like that, you probably don't need to connect your radio to an antenna. You can connect your radio to what we call a dummy load, which is a test antenna. It's an antenna that's designed to absorb the power coming out of your transmitter. And the one on the left is the famous Heathkit can antenna. It's a paint can with a 50 ohm non-inductive resistor inside and a bath of mineral oil. And that'll take 1,000 watts for a few seconds, and you can use that to make measurements at high power, or you can build your own dummy load as well. Just make sure you use non-inductive resistors here, and you can buy from Amazon and other places dummy loads for HTs and other devices to do testing. Computers are everywhere, and of course in ham radio as well. There are many, many uses of computers. Logging contacts. Most people, hams now, don't keep a paper log. They have a log in their computer. There's free computer logging software available, and there's also paid software. Sending and receiving Morse code, we talked about that. Digital signals like PSK31 or FT8 are all using computers. The software-defined radios like my Flex 6600, you can use a computer to control and display that. You can also interface computers with your antenna analyzer. You can operate your station remotely over the internet. All of these things have evolved over the years with computers and ham radios. And it all started with computer sound cards. Remember sound cards? They were used for the early digital modes, PSK32, to convert audio to digital. So you could use the sound card built into the computer, which would provide an input and an output to the computer. The only problem is it didn't provide any push-to-talk control for the radio. So along came these radio interfaces, which were actually sound cards in a box, usually with a USB interface. So the signal link was one, West Mountain Radio was another, and you could actually then use these to send audio from the radio to the computer, audio from the computer to the radio, and that all-important third thing, the push-to-talk, the transmit activation, which is what you needed to do. These were very popular, and then manufacturers got smart and they built them in to the radios. So the ICOM 7300 is a very good example. This is a very popular, the most popular amateur radio transceiver. Over 100,000 units have been sold. It's an HF transceiver from 160 to 6 meters. Nice spectral display on the front, and if you look around the back panel, it's got a USB jack here. It's got a built-in sound card inside, and it's got the control circuitry that you can trigger it to go into transmit. Built-in sound cards are something that all modern radios today have, but we used to use those signal links and others to get the older radios to work. And transverters. You've got that ICOM 7300. It'll work up to 6 meters, but you want it to work on 2 meters, or you want it to work on 70 centimeters. How do you do that? Well, you can add one of these boxes. A transverter converts both transmit and receive to a different band. So in this case, you'd tune the 7300 to the 10-meter band, and it would translate those signals up to 2 meters, for example, if you got the 2-meter box. That's a transverter that is used to change both receive and transmit to a new band. Okay, more questions. So why should you not set your transmit frequency to be exactly at the edge of an amateur band or subband? Remember from the previous? Read carefully.
B.
B is true. A is also true, and C is also true. So this is one of those, all of these choices are correct. You want to compensate for all of these various factors. But I'm glad you got B. That was the one we were emphasizing. All right. What would cause your FM transmission audio to be distorted on voice peaks?
Charlie.
It can be as simple as you're talking too loudly, and what you can do is just move the radio away from you. And what is the purpose of a squelch function?
B, Bravo.
Yeah, we heard it on the Baofeng. When I push that button on the side, you got that horrendous static. It mutes the receiver audio when a signal is not present. And what is an electronic keyer?
Charlie.
Yes, it's a device that assists in hand sending or manual sending of Morse code. And what is the effect of excessive microphone gain on single sideband transmissions?
Bravo.
You will get distorted audio, get people talking to you saying, hey, you sound awful, turn your gain down. So which of the following can be used to enter a transceiver's operating frequency?
A, Alpha.
Yes, so to change frequency, you could use the keypad or you could use the big knob. And how is squelch adjusted so that a weak FM signal can be heard?
Alpha.
It's a long answer that says turn the squelch off. Set the squelch threshold so that the receiver audio output is on all the time. Oh, thanks so much. So what is a way to enable quick access to a favorite frequency or channel on your transceiver?
Bravo.
Yep, store it in a memory channel. We have memory channels on HF transceivers and on the HTs. And which of the following controls could be used if the voice pitch of a single sideband signal returning your CQ call seems to be too high or too low?
Delta.
Yeah, or the net operation where the one guy is off frequency, you use the receive incremental tuning, also known by some as a clarifier. So what is the advantage of having multiple receive bandwidth choices on a multi-mode transceiver?
Bravo.
Permits noise or interference reduction by selecting a bandwidth matching the mode. You get the best signal to noise ratio. And which of the following receiver filter bandwidths provides the best signal to noise ratio for single sideband reception?
Charlie.
If you had a single sideband radio, you'd see this is a common bandwidth, 2400 hertz, smaller than 3000 hertz, which we said is the transmitted bandwidth, so that really you're only receiving modulated signal when you go to 2400 hertz. No noise outside of that. All right. What is the result of tuning an FM receiver above or below a signal's frequency? What do you think?
Bravo.
It's not Bravo because an FM transmission doesn't, it has sidebands, but
Right.
Delta.
it's even, so yeah, distortion, it's going to sound horrible. If you ever tried to listen to an FM broadcast station in your car and you're slightly off frequency, it doesn't sound good. Distortion of the signal's audio. And which term describes the ability of a receiver to detect the presence of a signal?
Bravo.
And you know what I never did? I never spotlighted my video for you folks in the Zoom classroom. You got to remind me of this. because you probably have a hard time seeing it, or maybe you pinned me. But okay, there we are. Yes, sensitivity describes the ability of a receiver to detect the presence of a signal. I apologize. All right. Which term describes the ability of a receiver to discriminate between multiple signals?
Charlie.
Yes, selectivity. So we want sensitivity and we want selectivity. And what device converts the RF input and output of a transceiver to another band? Yes, that's the transverter box. We looked at the one there was from Elecraft. And what is the function of a transceiver's PTT input?
Bravo.
Bravo is correct. Electrically, it's what happens is you actually ground a wire and that puts the radio into transmit. And what is the function of the single sideband CW-FM switch on a VHF power amplifier or power brick?
Bravo.
Yes, it sets the brick for the proper operation in the selected mode. Linear mode for single sideband signals and nonlinear for FM or CW. So what device increases the transmitted output power from a transceiver?
P.
Yes, an RF power amplifier, also known as a linear amplifier. And where is, not to be confused with, where is an RF preamplifier installed?
Alpha.
Think about my old Heath Mohawk and the fact it couldn't hear very well on 15 and 10 meters. You install that between the antenna and the receiver, the RF preamplifier. What can you do if you're told your FM handheld or mobile transceiver is over-deviating?
Delta.
Deviation is the process of adding modulation to an FM signal. And remember, with FM, it's all about the amplitude. So if you're deviating too much, just talk softer or talk farther away from the microphone. And what is the primary purpose of a dummy load?
A alpha.
Yep, to prevent transmitting signals over the air when you're testing your equipment. And what does a dummy load consist of?
Bravo.
A non-inductive resistor mounted on a heat sink or in a heat bath. Very good. All right, you've been great. I lied, Bruce. We do have an intermission. So you've been great. Let's take 5 minutes and get up and stretch and move around, and we'll come back with section 5.3, digital communications.
Hey, on that signal meter.
And welcome back. So glad to have you with us. Hope you get a chance to move around and stretch a little bit. We're going to go into section 5.3, digital communications. And some of the first digital modes, well, some folks say that Morse code is a digital mode. Okay, that could be argued. And radio teletype. And both of those got their start as electromechanical devices. Here's an old radio teletype printer and typewriter or system, a transmission system. There may be a paper tape reader there as well. Well, things evolved from electromechanical up to electronic. Here's a radio teletype system that was all electronic, dedicated to radio teletype, not a computer. Nowadays, there's computer software and programs that you can use to send and receive CW and radio teletype. I consider probably the first digital mode really to be the packet radio that we talked about before. The timing was such that telecommunications connections to bulletin board systems was going on, and we were using ham radio to get the same effect. And packet radio was mostly on VHF and above. It used that box in the middle called a terminal node controller to connect between a terminal or computer. And it used a networking protocol called AX25. X25 was the commercial protocol, and A stands for amateur, so amateur X25. And the packet that we saw earlier had a header and a checksum and the data information, and then the ability to check for errors and make a request, an automatic request. If it was received with errors, send it again. So packet radio evolved eventually to what we know today as the APRS system. Automatic packet reporting system. It's a packet radio, but it adds a GPS receiver as well, which gives the latitude and longitude of where you are. It can also transmit short text messages if you are using it to support a marathon or something like that. It can also give position data. And you can go to this website, APRS.fi, and move the map to your area, and you can see amateur radio operators moving around your area in their vehicles or with portable APRS systems. It's a way that you can track locations voluntarily here of folks. Some radios have APRS built in, others you have to add it on. Now, another mode of digital communications, I mean, we're all sending and receiving email. That's passé now. But you can send email via radio as well using something called the WinLink system. And you can go to the URL there, www.winlink.org, and get more information. It's on HF and VHF and UHF, and it uses what they call gateway stations. You can radio into a gateway station on their frequency. They'll receive your email and forward it on to the public internet. So you can actually send emails using amateur radio and this system. Other digital modes, some are more common than others. Data modes are limited to 300 baud. Remember that really slow rate on HF. Radio teletype uses a 5-bit code known as baudot. There's packet radio on HF called PACTOR, and the Windows message over radio system and PSK31. They were all popular digital systems, some more so than others. But the one that has taken the world by storm is this one, FT8. And this is the software, WSJTX. There's information at that URL there, but actually the next slide will show you where you can download free the FT8 software. Joe Taylor is the guy in the upper right-hand corner. He's one of the two developers. Steve Frank was the other. There was a third a British guy, but he doesn't get a lot of credit. Anyway, they came up with FT8 originally years ago to do meteor scatter communications. And it evolved over time into this thing that it changes the ability of stations to receive weak signals. It trades computer time for signal strength. So during the sunspot lull about 5 years ago, where bands were really totally dead, FT8 could actually hear signals that you couldn't hear with your own ears. So FT8, a very important thing. Here's the URL where you can find it on SourceForge. JT65 was the first mode, and that's still included in the software. Whisper, propagation software, is also popular, but FT8 is the big one. And FT8, F is for Steve Frank, T is for Joe Taylor. Joe Taylor is a Nobel Prize winner for physics at Princeton, I believe. They're the co-developers. An FT8 signal only occupies 50 hertz of bandwidth. Remember I said a CW signal was 150 hertz? So an FT8 signal is even narrower. So that's why FT8 is actually taken over for the most power efficient mode that you can have. It's a weak signal mode, but you can still use high power, and it's great for DXing. Now, the old timers in ham radio will say, however, it's a contact, it's not a conversation. It's true. In this mode, the only things you exchange are your call sign, your grid square locator, a signal strength report, and you say 73 to the other guy. That's it. That's about all you can do. There are some, derivations of the, but and you can't ask about the weather. You can't talk about, no. So old timers, complain about that. Number one. They also complain about, some people hacked the software so that, their stations could be on the air automatically. That's not allowed. So here's a slide here. How is your FT8 working out for you? Well, my computer is working Asia right now. Anyway, with digital modes, we have these terms that we want to know about. Bit error rate. You want to have the lowest bit error rate possible. You want to get all the bits through. A parity bit in packet radio, for example, is used to help detect errors. A digipeater, a terminal node controller, can be a digipeater used to relay digital communications. Satellites can carry digipeaters as well. There are node stations that can have high frequency data, high data rate links that can transmit digital data. And phase shift keying, PSK31, was super popular up until FT8 came along, and then you have very little PSK31 going on anymore. More digital terms are a radio message server used in the WinLink system. We talked about GPS used with the packet radio. Old computers used to have COM ports with DB9 and DB15 connectors on them. You have universal serial bus connections nowadays, but if you're interfacing to old equipment, you might have to deal with that. And there are still bulletin board systems out there, believe it or not, that you can log into and check on things. So when we talked about the gateway station. Did you know that you have a digital signal going on in your house probably 24 hours a day? Wi-Fi. IEEE 802.11, also known as Wi-Fi, is operating probably on your home router for the internet on the 2.4 gigahertz band. That's 13 centimeters. That's the 13 centimeter ham band. So it's a shared band where hams can actually do experimental long-range connectivity experiments by modifying commercial routers like this one from Linksys to use specialized software. We're not going to go into more details on that, but just know that Wi-Fi is a shared band. All right, some questions. How are the transceiver audio input and output connected to a station configured to operate using FT8? Try to remember the software I talked about there.
Bravo.
Joe Taylor, yeah, Bravo. To the audio input and output of a computer running Joe Taylor's software, WSJTX. Weak signal Joe Taylor. All right, what signals are used in a computer radio interface for digital operation? What three things do you need?
Charlie.
Receive audio,
Yeah.
transmit audio, and push-to-talk or transmitter keying. And which of the following connections is made between a computer and a transceiver to use computer software when operating digital modes? They're asking here, an output has to go to an input.
Charlie.
Yeah, in this case, the computer's line in would connect to the transceiver's speaker connector. That's one way that you could get tones into the computer. And what is an amateur radio station that connects other amateur stations to the internet? What do we call that?
C. Charlie or A, gateway?
It is a gateway, indeed. Part of the WinLink system. And which of the following is a digital communications mode? Read carefully.
Delta. D.
Yep, packet radio, yes. IEEE 802.11, that's Wi-Fi, yes. FT8, yes, all of those choices are correct. And what kind of data can be transmitted by APRS?
D. Delta.
Yeah, all of those. GPS position data, text messages, and weather data, if you had a weather system connected, all of those. So which of the following is an application of APRS?
Alpha.
Providing real-time tactical digital communications in conjunction with a map showing the location of stations. So that if you had a race going on with cars that had APRS transmitters in each of the cars, you could follow the car's locations, for example, in Baja or something like that. So what does the abbreviation PSK mean?
Bravo.
Phase shift keying. And which of the following is included in packet radio transmissions? Read carefully.
Delta.
Yes, all of those are part of a packet radio transmission. A checksum that permits error detection, a header that contains the call sign of the station in which the information is being sent, and automatic repeat request in case of error. All of those choices. And which of the following operating activities is supported by digital mode software in the WSJTX software suite?
Delta.
All of those. Got started with meteor scatter. He's added Earth, Moon, Earth, and weak signal propagation, all of those choices. Download the software, it's free, it's interesting. So what is an ARQ transmission system?
Charlie.
It's what packet radio is. It's an error correction method in which the receiving station detects errors and then sends a request for retransmission. Hey, I didn't get it, send it again. ARQ, automatic request. Which of the following best describes an amateur radio mesh network? I didn't talk about this specifically, but you saw that Linksys router that could be modified.
Alpha.
It's an amateur radio-based network using commercial Wi-Fi equipment with modified firmware. They call it a mesh network. And using amateur frequencies, it would be an amateur radio-based mesh network. So what is FT8?
Bravo.
It's a digital mode capable of low signal-to-noise operation. I mentioned before bands were dead, but still signals could be heard by the software, not by humans. All right, section 5.4, power supplies and batteries. Some radios have built-in power supplies. My ICOM IC7760, I just plug it into the wall. It's got a built-in power supply for everything in there. But a lot of ham radio transceivers were originally designed for use mobile. And so they're looking for 12 volts, which actually is 13.8 volts. That's the standard. So most ham radios, if they're 12 volt, they need a 12 volt power supply, or 13.8 volt power supply. And you could operate the radio on a battery, but it's kind of in your house. That's kind of awkward and whatnot. So you can buy power supplies. You'll see them at ham fests, and there are two main types. Linear power supplies, the old power supplies with big heavy iron transformers inside, step-down transformers. They're really heavy. You know it's an old linear power supply if you try to pick it up and you can't. It's really heavy. Whereas new modern switching power supplies, like the Yelenko one here on the right, are much lighter weight because they use switch mode technology and high frequency transformers, which are very lightweight. So mobile transceivers for VHF and UHF, they're typically no more than 50 watts output. So you can get by with a power supply of 13.8 volts with 15 amps of current. That's nominally okay. For high frequency radios, so it can be 100 watt radios, you need to double that. 13.8 volts still, but 30 amps out. And both of these are regulated voltage that will hold the output voltage of the power supply constant at 13.8 volts. All right, learn from Gary's mistake. Come back to me just for a second. So I needed a power supply for, actually it wasn't for ham radio use, it was for a security camera system that I had at my old homestead. They came with wall warts for all the cameras, and I had about 6 or 8 wall warts that were powering these cameras. That's no good, and they were all 12 volt, so why don't I just get a 12 volt power supply? And okay, Astron is a very good name for power supplies, and they're expensive. And Gary is a cheapskate. So I went on Amazon and I said, oh, here is a Chinese power supply. It's rated at, I think 15 amps or 16 amps. And so, yeah, that should be fine. Yeah, let's get that. It's much less, much cheaper. So I did. Come on back to the laptop. This is what I bought. You get what you pay for. This power supply, even though it had a nice sounding name, Audiotech, and it worked initially just fine, in a matter of a week, the regulator system failed, and instead of having 12 volts or 13.8 volts output, it had 21 volts. It fried all my cameras. So the lesson here is don't buy inexpensive, I say cheap Chinese power supplies. It's just not worth it. Get something reputable, something that somebody else would recommend. Astron is always good. So, and other manufacturers, Yelenko and others are good as well. All right, car batteries. We're not talking about EVs, but lead acid batteries for normal combustion engines. Nominally 13.8 volts when they're charging. It charges from the vehicle alternator. Did you know that when you're charging a lead acid battery, it releases hydrogen? And hydrogen is flammable, even explosive. So charging too fast can release high levels of hydrogen, an explosive gas. So just keep that in mind, whether you're going to a field day and you're charging batteries or your car. Also, in your car, there are lots of sources of noise. So if you're going to put an HF radio in your car, you're going to have to deal with noise coming from the engine, from the alternator, from spark plugs. Various panels in the car may not be properly grounded or bonded together. You need to run the power connection for the radio all the way back to the battery. you know, back in the day, you used to be able to use a positive lead to the battery and just connect anywhere on the chassis. You can't do that anymore. It may work briefly, but you'll get lots of noise, and so you want to run the power leads all the way back to the battery. Or if your engine has a current sensor, you want to keep that in mind. Maybe consult with the manufacturer. So batteries in the car, noise sources in the car. Batteries at home for electronic equipment, just keep in mind that some batteries, nickel cadmium, nickel metal hydride, some are rechargeable, some are not. This is kind of small on my screen here. The old carbon zinc batteries, you know, the flashlight batteries, no, you can't recharge those. Alkaline batteries, no, you can't recharge those. So keep that in mind, that if you're going to be using a system that requires rechargeable batteries, get the proper type. One of the more common types now is the lithium iron phosphate batteries. They're very popular because they're very lightweight compared to a lead acid battery. They're rated with an output voltage, in this case 12.8 volts, and an amp hour rating, 100 amp hours. And you can determine the runtime of your equipment if you know the average current draw of your equipment and divide that into the amp hours, and it'll give you the runtime in percentages of an hour. So if you got 100 amp hours and your equipment draws 1 amp, well then you should get 100 hours of operation. So keep this formula here in mind. And if you're going to be powering equipment like for field day or at a work site or something like that, generators are useful. Inverters, converting 12 volt to 120 volt, they can be useful. Pretty much all inverters anymore are pure sine wave. It's hard to find modified sine wave anymore. But whether it's a generator or inverter, you always want to keep in mind, well, how big do I need? You always want to consider, you know, the RF output stage of the radio. How efficient is it? That 100-watt radio may actually consume 200 or more watts when you're transmitting. So you always got to size for that, and also if you've got anything that's going to have a lot of inrush currents, like an amplifier or something like that, you've got to factor that in. You also got to factor in the wire gauge that you're going to be using. Each wire gauge has a certain ampacity, the kind of the maximum current it can carry. The goal is to get a wire big enough so that there's no voltage drop across the wire from the power source to the radio, say, for example. So always keep that in mind to minimize voltage drop. All right, some questions. Which of the following is an appropriate power supply rating for a typical 50-watt output mobile FM transceiver? What do you think?
Delta. D.
Yeah, they say 12 amps, I say 15, but the 13.8 volts at 12 amps, okay? And why are short heavy gauge wires used for transceivers' DC power connection?
A, alpha.
Yeah, to minimize voltage drop. And how can you determine the length of time that equipment can be powered from a battery?
Bravo.
Divide the battery's ampere hour rating, 100 ampere hours for example, by the average current draw of the equipment. B is correct.
About what are those radios draw?
On transmit, a mobile radio will drop to 12 to 15 amps. Much less on receive. All right, here we go. Where should the negative power return of a mobile transceiver be connected in a vehicle?
Alpha.
Yes, at the 12-volt battery chassis ground. And which of the following battery chemistries is rechargeable?
B. Oh,
B is true.
D.
Yeah, all of those can be recharged. Lead acid or nickel metal hydride, all is possible. All right, of these, which of the following chemistries is not rechargeable?
Bravo.
The old flashlight batteries, carbon zinc. And what type of circuit controls the amount of voltage from a power supply?
Regulator, A.
Yeah, it's what failed in my cheap Chinese power supply that gave me 21 volts out and no good. So what hazard is caused by charging or discharging a battery too quickly?
Alpha.
Overheating or outgassing of hydrogen. And that, ladies and gentlemen, is the end of chapter 5. But wait, I've got some more that I want to bring to your attention. There are 3 websites that you can use to review test questions. We've now completed 5 chapters, 2 through 5 anyway. So you can go to the American Radio Relay League's exam review website here and use it to review test questions. There are also hamstudy.org and QRZ.com also are places you can go to review. If you want to go to the ARRL site, this is what it looks like. You sign up for a free account just so that they can help you when you log in, tell you how you're doing, tell you what you've taken so far, etc. We're going to actually give you an example or show you an example how to use this when we have more time. I'm going to get you out 15 minutes early, but before we go, are there any questions or comments? I'll go ahead and take the spotlight off here in the Zoom classroom. Any questions?
I do like that first website, ARL, for the study questions.
Yeah, they're the ones we recommend most.
I started on Monday doing chapter 5.
All right.
Yeah.
Okay, folks. You've done great. Thank you for your attention tonight. Chapter 6 is next. Watch for an email from me tomorrow morning with links for the handouts, etc. All right. Until next week, 73, y'all.
Thank you, Gary.
73.